Hello and welcome back to the workbench. I'm Dustin with Motbots, and today we're going to create a true sensor to logic to actuator system. In this project, we'll build a circuit that reacts to the real world. Instead of blinking LEDs like we did in the previous project, this circuit senses temperature and makes a decision, just like real electronics inside robots, computers, and machines. If you've completed the LED blinker circuit from part 3, congratulations! You've already built a dynamic circuit. Now it's time to level up your game with this circuit. So for this project, we're putting together what I call the 555 temperature controlled fan controller using a thermistor, 555 timer, and a MOSFET, along with some other necessary components. The 555 temperature controlled fan controller, once finished, will be a circuit that cools when the temperature rises with the use of a 12-volt DC fan and a potentiometer. The DC fan turns on when the circuit gets warm and turns off when it cools down. The fan stays off when the circuit is cool until a certain threshold is reached when the circuit warms up. Then the fan turns on. The fan stays on when the circuit is warm until a certain threshold is reached when the circuit cools down. Then the fan turns off. A potentiometer lets you adjust the temperature threshold. It uses a 555 timer as a Schmitt-Trigger comparator, so it doesn't chatter on and off around the threshold. A MOSFET handles the fan current safely. Unlike a simple comparator, a Schmitt-Trigger has two voltage thresholds, an upper threshold where the output switches on, and a lower threshold where the output switches off. Between these two thresholds, the output does not change, even if the input wiggles around. This gap between thresholds is called hysteresis. Hysteresis is a small intentional dead zone that prevents a circuit from changing its output too easily. Instead of switching on and off at the same point, a circuit with hysteresis turns on at one level and turns off at a different level. This separation between switching points makes the circuit stable and predictable. For this project, we're using a thermistor as part of the sensor node of the circuit. A thermistor is a special type of resistor whose resistance changes with temperature. We're going to use a 10K NTC thermistor, where NTC stands for negative temperature coefficient, meaning the resistance decreases as temperature increases. A thermistor by itself only changes resistance, not voltage. To make it useful, we place it in a voltage divider with a regular resistor. As temperature rises, the thermistor's resistance drops. This causes the divider's output voltage to change. That changing voltage represents the current temperature. Heat becomes an electrical signal that the circuit can understand. This video here is not meant to walk you through with how and where to place your components and jumper wires onto your breadboard. I proceeded with this breadboard build like I do with many others, with no particular planning involved. All I did was follow my schematic diagram as I wanted the circuit to be, did the best I could to follow the diagram, and placed my components as best as possible on my breadboard. This is a prototype circuit. What you see is the result of the first time of my setup of this circuit, at least for this iteration of the circuit you see here that actually worked for me. I did make others that didn't quite work the way that I wanted, but this one is the one that worked for me. It's not pretty, but it works. The schematic diagram for this circuit can be obtained from the article associated with this project at the website, motbots.com. I'll leave the link to it in the description of this video. A good way to get to grips with our circuit diagram is to think of it as being in three major sections. The power supply section, as you see here in red, the power enable stable section, seen here in yellow, and the sensor section, seen in green. Let's start with the power supply section. Okay, as you can see here in front of you, this is our 555 temperature controlled fan controller circuit on the breadboard. I'm going to start off with going over the power supply section, or the power rails of this circuit, and that would be the very first thing that I would start off with when I'm placing components on the breadboard, is getting my power supply set up for the board. So I'll start here at this red wire here. This red wire here is going to be where I'm going to connect the positive power supply at, or the positive side of the 12 volt power supply. Currently it's obviously not hooked up right now, but this is where the positive is going to go. That red jumper wire is already attached to this first point on the positive side of the power rail of the breadboard. Continuing down, I want these rails, at least the positive rails here, to continue from the upper part of the breadboard down to the lower part of the breadboard, because there's a gap here that separates the upper portion from the lower portion or points of the power rail. So I'm continuing that positive supply through this orange jumper wire here down to the lower points on the positive power rail. Now I'm connecting the right side positive power rail to the left side positive power rail of the breadboard with the use of this orange jumper wire here. So these points on this side are now connected to the right side points. At least the bottom portion of these points here are connected to all these points on the right side for the positive supply. Continuing up, there is an orange jumper wire here, continuing the lower portion of the positive power rail points here to the upper positive power rail points that continue all the way up to the other side of the breadboard here. So at this point, we have all of the positive power rail points connected to each other, and now we need to make sure that the negative power rails are connected to the ground of the power supply, and this brown jumper wire here will be connected to the negative of our power supply later, and that brown wire is connected to this top point on the negative power rail points on this left side of the board. And just like I did with the positive, I am continuing the connection of these points all the way through. This little green jumper wire here helps me connect the upper to the lower points, all the way down to this larger green jumper wire here, which continues that ground or negative supply connection all the way throughout the negative supply rail on the right side and the left side. So that allows us, for when connecting the power, to be distributed all throughout the breadboard, at least on the right and left side power rails of the breadboard. Looking at the top portion of the breadboard here, I have a bulk capacitor here. A bulk capacitor is used to help keep the circuit's voltage stable and clean. The bulk capacitor sits between the plus 12 volts and the ground of our power supply. I'm using a 10 microfarad electrolytic capacitor. That's a polarized capacitor, so we need to make sure that its leads are placed in the proper orientation. We place the capacitor where the power supply first enters the breadboard, or as close as practical, so it can absorb sudden current demands and smooth out voltage dips caused by the switching loads, such as the fan we're using in this circuit. Without this capacitor, brief current surges from the fan could momentarily disturb the supply voltage between the 555 timer, and we'll get to the power supply to the 555 timer here in a little bit. So the way that this bulk capacitor is positioned on the breadboard is I've placed it across the gap, or the center gap of the breadboard. The center gap is isolates both the left and right side of these center points, or the center section of the breadboard. I have the cathode of this capacitor at point row 4, column E, and I have its anode at point row 4, column F, at least in my case. You can place these components wherever you want to, but this is how I placed mine. And in line with that cathode lead of the capacitor, I've placed this red jumper wire that's placed on row 4 here at point row 4 column A, which is in line with that cathode lead, and I've placed the other end of that red jumper wire in one of the points on the positive power supply here on the right side of the power rail. And on the left side, I've placed a brown jumper wire that one of its ends or leads is placed at row 4 column J, which is in line with that anode lead of the capacitor, and the other side of that jumper is placed at one of the points for the negative supply on the left side negative power rail here. So I have this capacitor set in parallel with the incoming power supply that will be connected to the circuit later. Okay, continuing on to the power enable stable section of our circuit. Looking at the schematic diagram, we're considering the power enable stable section as the part of the circuit that includes the 555 timer and the connections to its legs or leads. That's pins 1 through 8. Okay, now with the camera views at a different angle now and a little closer view of the 555 timer. Here it is right here. I don't know how well you can see it, but if you look at your 555 timer chip, there is a dimple. If I have it in the orientation as it is right now, the dimple is in the upper left hand corner of the chip, and that notifies us that that dimple is adjacent to pin 1 of the chip. So starting here is pin 1, then we have pin 2, pin 3, and then pin 4, and then across pin 4 on the lower right hand side of the chip we start at pin 5, pin 6, pin 7, and pin 8. And I've placed this chip on my breadboard for its left 4 pins to be placed at rows 11 through 14 at column F, and its right side pins at rows 11 through 14 on column E. To set up the 555 timer for power, I've placed a white jumper wire here that has one of its ends in a point on the right hand side positive power rail, and the other end of the white jumper wire is placed at a point on row 11 in line with pin 8 of the 555 timer, and that is the VCC pin or the positive power supply pin. And then across from pin 8 is pin 1, and I've placed a blue jumper wire with one of its ends placed on a point on the left hand side negative power rail, and the other end of that blue jumper wire is placed on a point on row 11 that's in line with point 1, and point 1 is the ground pin of the 555 timer. I also placed a decoupling capacitor that is across pins 1 and 8, or the ground pin and VCC pin, and I've gotten it as close to the 555 timer as possible. In this case, I placed the decoupling capacitor across the center gap of the breadboard. One lead is at row 9 column F, and the other lead is at row 9 column E. And I've placed these orange jumper wires that are in line with each of the legs of the capacitor. And on this side, this orange capacitor, or this orange jumper wire, is in line with pin 1, and this orange jumper wire is in line with pin 8, forming a connection from across pins 1 and 8 across the ground and VCC pin of the 555 timer. We do this to keep the circuit's voltage stable and clean, especially when parts of the circuit switch on and off. The decoupling capacitor acts like a small local energy reservoir. If the supply voltage momentarily dips, then the capacitor supplies current. If a voltage spike appears, then the capacitor absorbs it. This happens extremely fast, much faster than the power supply or long wires can respond. A 100 nanofarad or 0.1 microfarad ceramic capacitor is ideal because it responds very quickly to fast voltage changes. It's effective at filtering high frequency noise, and it works best when placed physically close to the IC's power pins. That's why we mount it near pin 8 and pin 1. That's the VCC pin, or positive power supply pin, and the ground pin, which is pin 1 of the 555. Next, we'll move on to keeping the reset pin of the 555 always enabled or on. Before the 555 timer can make any decisions, it must be placed into a known stable operating state. Several pins of the 555 are not part of the sensing or output logic at all. Their job is to simply power the device and keep it enabled. These are often referred to as the always on pins because they are wired the same way in many different 555 applications. The 555 timer requires a power source to operate. Pin 8, or the VCC pin, supplies the power to the internal circuitry. Pin 1, the ground pin, provides the return path for the current. Together, these two pins power the entire device. Without them, nothing else in the circuit can function. The reset pin, pin 4, allows the 555 to be externally disabled. If this pin is pulled low, the output is forced off regardless of the input conditions. In this project, we want the 555 to run continuously. So what I did for pin 4 is I took a long enough red jumper wire here. I mean, you can use any color you want, but mine happens to be red. I took a long enough jumper wire to reach from pin 4 over to pin 8 of the 555 timer. So in connecting pin 4 to pin 8, remember pin 8 is the VCC pin, that is the positive power supply to the 555 timer. So as I said, the reset pin, or pin 4, allows the 555 to be externally disabled. If the pin is pulled low, the output is forced off. That's regardless of the input conditions. In this project, we want the 555 to run continuously, and to do that, that's why I connected the jumper wire from pin 4 over to pin 8, so there's always power being supplied to pin 4, or to the reset pin. And just as I said, this ensures the timer is always enabled and free to respond to the sensor voltage, which we'll get to here in a little bit. So moving on to the control pin, that's pin 5 of the 555 timer. That's this lower right hand pin the lower right hand pin of the 555 timer. This is the control pin, and it provides access to the internal reference voltages used by the 555's comparators. In most applications, we don't need to adjust these thresholds. Instead, we stabilize them by connecting a 10 nanofarad capacitor, so that's what this capacitor here is for, from pin 5 to ground. So as you see here, I have this 10 nanofarad or 0.01 microfarad capacitor with one leg at pin 5. That is the control pin of the 555 timer, and the other leg of this capacitor at pin 1, which is the ground pin of the 555 timer. This capacitor helps filter out noise and prevents false triggering caused by supply fluctuations. I used a 10 microfarad polyester film capacitor. This is its number is 2A103J. I used this because I couldn't find a ceramic capacitor of the same value at the time of making this circuit, so I just ended up using this type of polyester film capacitor. It didn't seem to matter which type I used, so either type should work just fine. I mean, we're just tinkering here anyway, so for the purposes of this project, this is totally fine, and it works fine. So pins 1, 4, 5, and 8 of the 555 are wired to keep devices powered, enabled, and stable before any sensing or output connections are added. With the 555 powered and enabled, we can now connect the sensor node and configure the timer to respond to temperature changes. Okay, so let's move on to the temperature sensor node. And now this is key to this circuit. A node is simply a point in a circuit where multiple components connect and share the same voltage. In this project, the most important node is the sensor node, and it's labeled Sense on the color block schematic. The purpose of the Sense node is to convert temperature into a voltage that the 555 timer can evaluate and make a decision about. Everything connected to the Sense node plays one of two roles. Some parts create the voltage, that would be the thermistor and the potentiometer, and other parts observe or influence that voltage. That would be the 555 input pins and the hysteresis resistor, which I'll get to in just a minute. Once we understand what the Sense node is responsible for, the individual wire connections become much easier to follow. I had to use a single turn potentiometer, which is quite large for this circuit, but it's all I had at the time of making it. I couldn't find a trim pot that was of equal size. This is a 10K ohm potentiometer, and I just could not find anything smaller. I know I have one somewhere, but I just couldn't find it, so I used this instead. So as I said, this is a 10K ohm potentiometer. This is a 10K NTC thermistor. Remember, NTC stands for negative temperature coefficient. So my sensor node on the breadboard here consists of the thermistor, this leg of this resistor here. This is a 100K ohm resistor that I'll get to here in a little bit. And that sensor node connection continues on row 22 on my breadboard to this yellow jumper wire here. And this yellow jumper wire is gapped across this center gap of the breadboard over to the other side, still on row 22. I know you can't see here because this large potentiometer is in the way, but that yellow jumper wire connects to the center pin of the potentiometer, and that is the wiper pin of the potentiometer. So just to go over that again, my sensor node is basically row 22 here. And on row 22, I have my thermistor, where one leg of the thermistor is at a point on the left-hand side negative power rail. The other lead of that thermistor is at point row 22, column J. And in line with that leg of the thermistor is one of the legs of this 100K ohm resistor. Also on row 22, it's at point row 22, column I for my case. And I have this yellow jumper wire that's also connected to row 22 in line with the legs of the resistor and the thermistor. And that yellow jumper wire is connected to the center pin or wiper of the potentiometer. So the whole row 22 here is considered my sensor node, and this is where I'll be taking some measurements with the multimeter later. This is what I'm considering my sensor node, that we can also see on the schematic diagram that's labeled the sense node, and that is the colored coded schematic diagram. So continuing from the established sensor node we just made, we'll continue to the connection to the node from pins 2 and 6 of the 555. Pin 2 is here on the left-hand side, and pin 6 is on the right-hand side of the 555 timer as we see it in the current orientation. So as I said, we're continuing from the established sensor node we made, and we'll continue the connection to the node from pins 2 to 6 of the 555. This is where we turn the 555 into a Schmitt-Trigger comparator. So what I did was I took another longer jumper wire, and in this case it's a red jumper wire. Like I said, you can use whatever color you want, but I took a red jumper wire and I connected one end of it on a point in line with pin 2 of the 555 timer, and I placed the other end of that red jumper wire at a point in line with pin 6 of the 555 timer, connecting pins 2 and 6 of the 555. From there, I continued that connection from pin 6 with this blue jumper wire, and I've brought it down to a point on row 17 in my case, and I'm going to be continuing that connection with another blue jumper wire on row 17 that goes to a point that's in line with the center pin or wiper pin of the potentiometer. So backing up, I've connected pins 2 and 6 of the 555 timer with this longer red jumper wire. This blue jumper wire is also connected in line with that red jumper wire that's connected to pin 6. That blue jumper wire is connected to row 17, and another blue jumper wire is connected at row 17 down to the wiper pin or center pin of the potentiometer, connecting the wiper of the potentiometer up to pins 6 and 2. And from that center pin or wiper pin of the potentiometer, if you remember, I just said that it's connected by this yellow jumper wire, which is connected to what I'm considering the sensor node on my breadboard, which is row 22 in this case. Okay, so the sensor node is here, and the wiper or center pin of the potentiometer is connected to that sensor node, as well as pins 2 and 6, which are also connected to the wiper of the potentiometer. Again, it's connected to the sensor node. So in this project, the 555 timer is not used to generate timing pulses. Instead, it's configured to act like a Schmitt-Trigger comparator, a circuit that switches cleanly between on and off based on the input voltage. Inside the 555 are two comparators and a latch with built-in reference levels at approximately 1/3 of the supply voltage and 2/3 of the supply voltage. This is why when taking voltage readings of the sensor node on our circuit and when adding heat to the circuit, we get a reading of around 4 volts when the fan kicks on, or about 1/3 of the 12 volt supply, and around 8 volts when the fan cuts off, or about 2/3 of the 12 volt supply. By tying the trigger pin and threshold pin, that was pins 2 and 6 from before, by tying those together, we force both comparators to observe the same voltage, the sensor voltage from the sense node. Remember, I just mentioned that we connected pins 2 and 6 together, and those are connected through these blue jumper wires to the wiper or center pin of the potentiometer to our sensor node here on row 22. When the sense voltage falls below approximately 1/3 VCC, or the positive supply voltage, in our case 12 volts, the 555 output switches on. When the sense voltage rises above approximately 2/3 the supply voltage, the 555 output switches off. Between these two levels, the output remains latched in its previous state. So the fan stays on if it were already on, and off if it were already off, until one of the two thresholds are met. This creates a built-in hysteresis window, which prevents rapid on-off switching when the input voltage changes slowly. We do this because the temperature changes gradually, not instantly. Using a 555 as a Schmitt-Trigger ensures the fan turns on decisively, stays on while the temperature is near the threshold, and turns off only after the system has cooled sufficiently. By tying pins 2 and 6 together, the 555 becomes a voltage decision device rather than a timing device. With the 555 now configured as a Schmitt-Trigger comparator, the next step is to connect the sensor voltage to this input and add hysteresis for stability. A high-value resistor, typically hundreds of kiloohms to a few mega ohms, is connected to the 555 output pin, or pin 3, which is right here, back to the sensor node. So what I did is I connected a 1 mega ohm resistor, that's this one here, and I connected one of its legs to pin 3 of the 555 timer, and the other leg of this 1 mega ohm resistor, I just placed it at a point on row 16 here at column J, row 16. There's nothing else connected on this row except for a blue jumper wire that's on the point row 16 column F, and all it's doing is bridging the gap between the two sides of the breadboard to the other side at a point on row 17. And remember, row 17 on this side, it's kind of hard because that jumper wire is in the way. But remember, row 17 on this side of the breadboard, it has these other blue jumper wires connected to each other, and those were the ones that we came from pins 2 and 6 that are tied together. So I have that 1 mega ohm resistor tied to pin 3 of the 555 timer, which also is connected through the blue jumper wires down back to the center pin or wiper pin of the potentiometer, which again goes back to the sensor node, or this row 22 on my breadboard. So the 1 mega ohm resistor is resistor R2 if you're looking at the schematic, and this resistor feeds a small portion of the output voltage back into the input. Because of this feedback, the voltage required to turn the fan on is different from the voltage required to turn it off. The circuit now has 2 switching points instead of 1. This creates a stable dead zone where small temperature changes do not affect the fan state. The reason why this all matters is because with hysteresis, the fan turns on decisively, it stays on until the system cools sufficiently, and it avoids rapid on and off cycling, or what we call chatter, where it can't really decide what it wants to do. So that resistor helps alleviate some of that because of the hysteresis that we've added into our circuit. So with hysteresis in place, the circuit is now stable and ready to safely drive the fan through a MOSFET, which I'm going to talk about next. The output of the 555 timer is not designed to power a motor or a fan in this case directly. While it can source or sink small currents, a fan requires more current than the 555 can safely provide. To handle this, we use a MOSFET as a low side switch. I happen to be using an NTE 2987 logic level MOSFET. This is what I had, so it's what I'm using. In a low side switching arrangement, the load, or the fan in our case, is connected to plus 12 volts. That's the voltage we're using from our power supply. The MOSFET sits between the load and ground, and the MOSFET controls whether current can flow through the load. When the MOSFET turns on, it completes the path to ground, and the fan turns on and spins. When it turns off, the path is broken and the fan stops. The reason why we use a logic level N-channel MOSFET is because it requires very little gate current and can handle much higher load current than the 555. The MOSFET basically acts like an electronically controlled switch. The 555 simply drives the gate of the MOSFET while the MOSFET does the heavy lifting. So I've switched you into a different position to give you a closer view of the MOSFET here. I know it's still difficult to see with all the stuff in the way, but we're going to try to do our best with what we have. So looking at the MOSFET here, the orientation of the leads for the MOSFET, starting with the face of the MOSFET where the lettering is facing us, starting from the left pin, that is the gate, the middle pin is the drain, and the right pin is the source pin. So I have placed my MOSFET on the points on column H, rows 17, 18, and 19 in my case. So that means that my gate pin is on row 17, column H, and I have this 100k ohm resistor, one of its legs in line with that gate pin of the MOSFET. I also, if I adjust the breadboard here where we can kind of get it an above view, I have you can barely see it, but I have a 100 ohm resistor here where one of its legs or leads is also in line with the gate of the MOSFET. And I will get to more on that here in a little bit. But I'm just trying to show what's connected to the pins of the MOSFET right now. So the center pin, as I said, is the drain pin, and the drain pin has this green jumper wire. It's a long jumper wire that I've placed here. We have not gotten to this jumper wire yet. It goes back to the fan, but just so you know, that's what this green jumper wire is here for, and it's placed on a point on row 18 in line with the drain pin of the MOSFET. And the far right pin is the source pin of the MOSFET. And I have placed this brown jumper wire here where one side of the brown jumper wire is at a point on row 19 in line with the source pin, and the other end of that jumper wire is at a point on the negative power supply rail here. So that's connecting the source pin straight to ground. Going back to the 100 ohm resistor, it's this back resistor back here. I mentioned that one of its legs or leads is connected to the gate pin of the MOSFET. I can't hardly see and the lighting's not that great, but this is the resistor back here. That's a 100 ohm resistor. One lead of it is at a point connected to the gate pin of the MOSFET, and I have the other leg or lead of that 100 ohm resistor going to pin 3 of the 555 timer. And this 100 ohm resistor, it's resistor R1 on the schematic, that is a gate resistor, and the gate resistor limits sudden current spikes into the MOSFET gate. And if we look over to this 100k ohm resistor here, I'm going to tilt it up just a little bit. I mentioned this resistor earlier where one of its legs or leads is in a point on row 22, and row 22 is our sensor node. This is our sensor node here. You can see our thermistor here. One of its legs is in a point on row 22, and this 100k ohm resistor here is its leg is connected in line with this thermistor. Again, that's the sensor node, line 22 or row 22. The other leg or lead of the 100k ohm resistor is in a point on row 17 in line with the gate of the MOSFET. And I don't know if I mentioned just yet, but this 100k ohm resistor is a gate pull-down resistor. This is resistor R3 on the schematic. And as I said, it's a gate pull-down resistor, and the gate pull-down resistor ensures the MOSFET stays off when the circuit powers up. So with the MOSFET driver in place, the circuit can now control the fan reliably without stressing the 555 timer. So what we're going to do next is one of the last steps we need to do on this circuit, and that is to place the fan onto the circuit. So let me switch the camera view again. Okay, now that I have you repositioned again in a different camera angle view, I'm going to be talking about adding the fan to the circuit now. I'm using a 12 volt DC brushless fan. It happens to be model number AFB 0712HB. And I think I might have scavenged this from an old computer from long ago. I'm not sure, but I think I probably did. Anyways, it has 3 wires. It has a red wire, a black wire, and a blue wire. The red wire is for power, the blue wire is for signal, and the black wire is for ground. We're just going to use the red and black wires for basic powering of the fan. I have a connector at the end of my fan, or at the end of the wires at least, and I could have cut it off, but I just chose to leave it on here and use jumper wires to shove in the terminals to be able to make the connections. So what I ended up doing is I took a yellow jumper wire, and that yellow jumper wire, I placed it into this connector, and it's in line with the red wire, or the power, the positive power supply of the fan, the red wire, connected to the yellow jumper wire. That yellow jumper wire is connected to a point on the left side positive power rail of my breadboard. And then I took a longer green jumper wire and connected it into the connector here in line with the black ground wire of the fan. And I placed the other end of that green jumper wire on a point on the breadboard. It just happens to be on row 33, column J. And from this point, I have other connections here. One being another long green jumper wire. That's the one I just discussed about, coming from the drain of the MOSFET. So I have the 2 long green jumper wires here, one coming from the ground wire or black wire of the fan, going to point row 33, column J on my breadboard. In line with that green jumper wire is the second green jumper wire going back to the drain pin of the MOSFET. And for the last order of business, I need to talk about adding the flyback diode across the fan. So a fan is an inductive load, which means it stores energy in a magnetic field while it's running. When the MOSFET suddenly turns the fan off, that stored energy has to go somewhere. If it doesn't have a safe path, it can create a high voltage spike that may damage the MOSFET or interfere with the rest of the circuit. So adding a flyback diode provides a safe path for this stored energy when the fan is switched off. During normal operation, the diode does nothing, but when the fan is turned off, the diode conducts briefly. This allows the energy to dissipate harmlessly instead of creating a voltage spike. I'm using a 1N5817 Schottky diode because that's what I had available, even though in the parts list of this project I recommend a 1N5819 diode. The two are very similar, and you could even use a 1N5818. I think that would be fine as well. They're all kind of similar to each other. I just happen to be using the 1N5817 Schottky diode because that's what I had. The reason why we placed the flyback diode across the terminals of the fan is to protect the MOSFET from voltage spikes, to reduce electrical noise, and to improve overall circuit reliability. The diode is oriented so it is reverse biased during normal operation, meaning it does not affect the fan while it's running. So in reverse bias means that I'm placing the cathode end of the diode at a point on the positive power rail of my breadboard, and I'm placing the anode of the diode in line with those two green jumper wires that I placed on row 33 here of my breadboard. And again, that one of these green jumper wires comes from the ground wire of the fan, and the other green jumper wire comes from the drain pin of the MOSFET. So with the flyback diode in place, the circuit is now protected and ready for safe operation and testing, which is what we're going to be doing next.